Hello everyone, Mr. Fawcett here, and we are back with another geometry lesson. Today we start our unit on probability, and we're going to start by talking about three main things actually. Two of them are in the title, one of them's not. But we're going to start with the fundamental counting principle, then we're going to look at permutations and combinations. Okay, let's actually look at these two do not problems. Get our brains thinking the right direction here. Pause video. See if you can evaluate both of those expressions for 1 and 2, and then come back and see if you're correct. Okay, so I think the first one's pretty straightforward, right? If we're just multiply all of those, 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1 is just still 120. Now, it also says, is there a way to write this expression without having to list out all the numbers? Well, you may think you may remember, if we start with a number and we multiply by every natural number less than that number. So here they start at 5, then they multiply by 4, 3, 2, and 1. That is the same thing as what we call 5 factorial. That's what this little exclamation mark means in math. It means factorial. So this is equal to this expression right here. Okay, let's move on to number 2. We're going to evaluate that expression. Well, you could multiply everything in the numerator, everything in the denominator, and then try to simplify, but it'd probably be easier to just factor out the common factors, right? Or simplify out the common factors. So that leaves me with just 7 times 6 times 5. That leaves me with 210. So just a quick way to do that would be to simplify first and then multiply rather than multiply and then simplify. Okay, let's look at number 1. So it says if a customer orders an entree, side, and drink, what are all the possible lunches they can order? And you can see over there on the right-hand side, it tells you what the entrees are, what the sides are, and what the drinks are. So we need to figure out all the different possible combinations. Well, I give you a hint. I say start by drawing a tree diagram if you were unsure of where to start. But I'm going to leave it up to you. So I'm going to have you pause the video and see if you could figure that out. Is there an organized way to figure out how many possible combinations there are of one entree, one side dish, and one drink? You can try a tree diagram. Maybe you know of a different way, but pause it and see if you're able to come up with that number. Okay, so hopefully you have a number off to the side here that we'll see whether it's correct or incorrect. If you wanted to start with a tree diagram, you can do these either vertically or horizontally. You could start with your entrees up top. So pizza, chicken, beef. And let's say I choose pizza. Well, I have 3 different options for side dishes. All right, I have coleslaw, and I'm just going to use CS, salad for fruit, S for salad, and F for fruit. Now, based on what side dish I choose, I have 4 different options for drinks. 1, 2, 3, 4. We'll do M for milk, P for punch, J for juice, and IT for iced tea. So you can see that this diagram would get complicated very, very quickly the more amount of options we have to choose from. And it's already pretty complicated, right? Just with 3 entrees, 3 side dishes, and 4 drinks. But you can kind of see what we do. So if we chose pizza and we chose coleslaw, well, there's 4 different options, right? Because there would be 4 different drinks. So by choosing this path, we have 4 different options. If we chose this path, we'd also have 4 different options. And if we chose this path, we'd also have 4 different options. So just by choosing pizza, right, if we were limited to pizza for an entree, there would still be 12 different meal options that we could choose. And this is going to look very similar for chicken and beef, right? There's actually going to be a total of 12 for chicken and there's going to be a total of 12 for beef. And again, I'm not going to go through and write out that entire tree diagram because I think we can kind of see the pattern just from pizza. But this would be a kind of what we call the brute force method, right? You're literally going through and you're writing out every possible example. It'll get you to the right answer. It just may take longer depending on, how many choices you have. That being said, you were only tasked with finding that number, so if you got 36 somehow or another, you are correct. But we're going to look at some easier ways of doing this rather than drawing out a tree diagram or just listing, one entree, one side dish, one drink until you are done. Maybe some of you already found another way, or maybe now that you know the answer is 36, you can kind of, figure out how to manipulate the number of entrees, side dishes, and drinks to get that. But that's where we're headed. First, though, let's start with some vocab dealing with probability. So we have an outcome. An outcome is a possible result of a probability experiment or situation. So an outcome in our previous example would have been pizza, coleslaw, and milk. Right? That's one possible outcome. You have an entree, you have a side dish, and you have a drink. An event is an outcome or set of outcomes. And an event is something that you may be asked to find the probability of. So in our previous example, you may be asked to find the probability of someone including pizza as their entree if they randomly picked an entree from the list of 3. You may be asked what's the probability of someone choosing pizza and coleslaw as part of their meal, right? That would be, a couple of different outcomes, right? Because you could have pizza, coleslaw, milk, or you could have pizza, coleslaw, juice, or pizza, coleslaw, iced tea, etc. So while an outcome is just one possible way or one possible thing that could happen, an event could include multiple outcomes. I just realized I forgot the S there. So an event could include multiple different outcomes. Now here's the fundamental counting principle. This is what is going to make our lives a lot easier. For a certain number of events, you can multiply the number of possible outcomes for each event together to find the total number of outcomes. So let's do this example, and then we'll apply it to the lunch example from up above. So let's say we have 3 events with the number of choices for event A being 4, the number of choices for event B being 5, and the number of choices for event C being 2. Well, then the total possible number of outcomes, right? If you were to choose something from event A, choose something from event B, and choose something from event C, there would be 40 different outcomes that you could come up with. Now, it may be easier for you to relate this to, something more real world like that menu problem. So let's do that. Let's walk through that example. And actually, let's jump up here. So there's work to do it down there, but I want to have this menu so we're able to see it. Although, you know what? Let's be a little creative here. Just put it here. There we go. Okay, so if we think of these 3 different categories as different events, right, we would have our entree or entrees as one event. And there are 3 options there. Well, the second event would be our side dishes. There are 3 options there. And our third event would be our drinks. And remember, an event is just a set of possible outcomes, right? So we can consider entrees an event, right? There's 3 different outcomes for entrees. There's pizza, chicken, or beef. For side dishes, there's also 3 possible outcomes. For drinks, there's 4. So if we treat each of these as their own event, well, to figure out the total number of outcomes, if we choose one from each category or each event, total outcomes, some of you probably know what we're about to do, is equal to 3 times 4, which is 36. Right, going to be much easier than drawing out a tree diagram, especially if these numbers are a lot larger. Right, if the number of entrees was 10, side dishes was 10, drinks was 15, well, you'd be here all day drawing a tree diagram, and then you'd have to count them, make sure you didn't leave anything out, etc. But it would be much easier just to do 10 times 10 times 15. Right, so the fundamental counting principle makes life a lot easier. You just need to identify the total number of outcomes for each event and multiply them all together. Let's do a practice problem down here. Let's look at number 2. And why don't you pause the video, read through it, and see if we're able to figure out how to apply the fundamental counting principle here. Okay, so it says if a license plate has 4 letters and 3 numbers, and both the letters and numbers can repeat, how many different license plates can be used? Note that the first 4 spots will be letters, and the last 3 spots will be numbers. Now, I know this isn't what every single license plate looks like. We just simplified it down. Certainly some license plates can have numbers in the first few spots. Sometimes they're all mixed up. We're just going to assume that all the license plates here follow the same format. Let's sketch a little diagram, though. It might make it a little easier to understand. I've got 7 spots here. First 4 must be letters. Second 3 must be numbers. So we're going to treat each of these slots as its own event. And if we can figure out the total number of outcomes for each slot or each space on the license plate, well, then we can multiply them all together to get the total number of outcomes. Well, for the letter spaces, we're going to assume we're just using English letters. There's going to be 26 possible options, right, for each space. For the numbered spaces, we're going to assume we're just doing single-digit numbers for each space, like a license plate. There are 10 possible digits, 0 through 9. So if we know all of the outcomes for each possible event, then we can just multiply all of those possible outcomes together, and that gives us 456,976,000 total outcomes. And you could think, right, if you were not if you were starting a country, but if you were the leader of the transportation authority, I'm not 100% sure what it's called for the United States, but there's probably different ones for each state. And you were trying to decide, okay, how many combinations of license plates do I really need? Right? Do I need 456 million? Or do I only need 6 million? Well, it might depend on how many cars are registered in your state, right? But that would give you an idea of how many spaces you needed on your license plate. It wouldn't make sense for us to have 10 different spaces on a license plate, because then it would be a ridiculous number of total outcomes, right? You could think about if I multiplied this number by 10 times 10 times 10, or 1,000, well, all of a sudden we're going to have a billion different combinations, more than a billion, right? 456 billion different types of license plates, and that would be unnecessary because there's not that many cars. But if I only had 3 spots for numbers or letters, well, even if I just used all letters, 26 times 26 times 26, let's quickly see what that gives us. Well, that's only about 17,500 different combinations. So when people are thinking about how many spots there should be on a license plate, well, they want to have about the total number of outcomes as there are going to be cars. A little bit more outcomes than total cars, right? You definitely don't want to be under because you don't want two cars to have the same license plate. But you also want to be efficient in how big your license plates are or how many slots you need, etc. Okay, let's look at another example, a little bit different though. This other one says, suppose a college had 3 different scholarships to give away, 1,000, 5,000, and 10,000. If there are 30 students to choose from, how many possible ways are there to choose the winners? Assume that no student can win 2 scholarships. Well, see if you can apply the fundamental counting principle here. See if you're able to set up 3 different events where you can apply that principle. And then we're also going to talk, this is where our discussion starts with permutations and combinations. But think about if we're able to apply what we've just learned to this problem. So it turns out you can apply the fundamental counting principle here. Each of these scholarship amounts would be considered their own event. Right, so we have $1,000. We have $5,000. And we have $10,000. And we would just need to think, okay, the amount of outcomes, let's say they start with the $1,000 scholarship. Well, there's 30 possible outcomes. Or maybe it makes sense to choose the first. It doesn't really matter which one we start with, but they're probably going to choose the best person first, then they're going to work their way down. So there's 30 students to choose from for the $10,000 scholarship. Now, once they pick a student, that student is no longer eligible for the second or third scholarship. So there's actually only going to be 29 students eligible, or 29 possible outcomes for the $5,000 scholarship, and then 28 possible outcomes for the $1,000 scholarship. So our outcomes are a little different here. We do have to take away somebody because they can't win more than one time. So we have 30 times 29 times 28. That gives us 24,360 total outcomes. Which seems like a lot, right? Only based off of there only being 30 different students that are applying. Now, while we can use the fundamental counting principle here, and it is pretty straightforward, this example actually leads us into a discussion of permutations and combinations. And these are what we use, or what we can use, when we have a group of something, maybe it's people, maybe it's things, and we're choosing a certain amount of things or people from that group. Now, the difference is permutations is when the order is important. Combinations are when the order is not important. So let's think about this above example. Right? Does the order, if I choose 3 people from the group of 30 to win these scholarships, does the order that I choose them in matter, or does it not matter? Well, take a second to answer that question. That'll kind of tell you whether this is an example of a permutation or a combination. If I had to choose 3 people from the group of 30 to win those scholarships, would the order that I choose them in matter? Well, the answer is yes. Right? Because all the scholarships are different amounts. If all 3 scholarships were 5,000, well, then the order wouldn't matter, right? Who I choose first would receive the same amount of money that I chose third. But when the scholarships are a different amount of money, then the order in which I choose does matter because it has an effect on how much money the students are getting. Another way to think of this is that, let's say I chose Jack, John, and we'll go Jonah. 3 J's. If I chose Jack, John, and Jonah, are there multiple ways for me to arrange those students so that one outcome is different from another, right? In a permutation, we would say yes, there are multiple ways to rearrange them, right? I could have Jack winning 1K, that stands for 1,000, John winning 5K, Jonah winning 10K. But then for the same three people, I could have Jack winning 5K, I could have John winning 1K, and I could keep Jonah winning 10K. And there's other combinations, right, that I could have with the same three people, or other outcomes rather. A combination would be, well, if I choose those three, it doesn't matter, how I arrange them, that is only going to count as one outcome. And that would be like if they all earned 5K. It wouldn't make sense for me to just switch around the numbers 5K because they're all winning the same amount. So the scenario up above, right, number one would be a permutation because the order does matter. Now, let's think about it from a combination perspective. Can you think of a situation in the real world where when you choose an amount of items or amount of people from an overall group, the order doesn't matter? So think about, you have a group of people or a group of items, and you're choosing a certain amount of those items. Is there a time when the order would not matter? Take a second, see if you can come up with at least one circumstance. Well, one example that popped into my head was if you're choosing teams, right? Let's say you're the coach for a soccer team and you have 30 different people try out. Well, you're going to choose maybe 18, we'll just say 18 of the 30 players. It doesn't really matter whether you call someone's name first or second, right? Because they're both going to make the team. Now, we're not talking about positions here. We're just talking about whether you're on the roster or whether you're off the roster, right? If I call 18 names, it doesn't matter the order that I call those names in because all 18 of those players are coming to the team. They're going to be on the roster. Another example may be you're at the store and you're trying to figure out what type of cereal to buy. Maybe there's 25 different kinds of cereal at the store, and you're going to choose 4 different kinds. Well, if you're going to end up taking home Cheerios, Kashi, let's go with, those are the 2 cereals that I eat, Cheerios and Kashi, so I need to think of some others. Reese's Puffs and Corn Chex. So what do I have there? Kashi, Cheerios, Reese's Puffs, and Corn Chex. If I put the Kashi in the cart first, and then the Cheerios, and then the Corn Chex, then the Reese's Puffs, well, that's the same as putting the Reese's Puffs, the Kashi, the Corn Chex, and the Cheerios in the cart, right, in that order. The order does not matter because you're going to be taking home the same 4 boxes of cereal. So again, we can have 2 different types of scenarios here. We can have one where the order does matter, like up above in the scholarship, and we can have a type where the order does not matter, like in the cereal example or the team soccer example. The idea is to be able to differentiate between the two. Now, when you're given an example that deals with choosing a certain amount of things from an overall group, if you can determine whether it's a permutation or a combination, well, then you can use your calculator to figure out, how many total outcomes there are. You can do these formulas by hand, and this kind of just shows you the type of math that's going on. It's kind of why we talked about factorials up at the very beginning of this lesson. But we're not going to focus too heavily on the formulas in this class. We're just going to focus on the difference between what a permutation is and what a combination is. And if you're able to identify the difference, then I am going to just allow you to use your calculator, which I'll show you in a second, to do this math for you. Let's look at one example. We already did the college one, so we're going to jump down to number 2. It says, for the problems below, identify whether the scenario represents a permutation or a combination, and explain your choice. Then find the number of possible outcomes. In a certain lottery, a person must correctly guess a string of 6 single-digit numbers without any repeats. Well, how many possible tickets are there, right? If they go to a gas station or wherever you buy lottery tickets, and you ask the attendant to print you out a lottery ticket, how many possible choices do you have? Right, so 6 single-digit numbers, and there can be no repeats. So first think about whether it's a combination or a permutation, and then actually we'll stop there because then I'll show you how to set this up in a calculator. Okay, so this would represent a permutation because there's a difference between 1, 2, 3, 4, 5, 6, and 3, 2, 1, 4, 5, 6. Right? You've chosen the same 6 numbers, but the order in which you wrote them down matters. Right? These would be 2 different tickets. Unless the lottery just said choose 6 numbers and you win, doesn't matter the order. Well, then it would be a combination. But if it's talking about a string, which implies 6 numbers in a row, it would matter whether you put the 1 in the first spot or the 1 in the third spot. So if we've determined that this is a permutation, because the order of numbers matters, well, this is the notation. We have a big P. On the left-hand side, we write the total number of numbers or things that we're choosing from. So in this case, well, if we're talking about single-digit numbers, there are 10 single-digit numbers we're choosing from, 0 through 9. We have to choose 6 of them. We are choosing 6. So that's the notation. This would say we're talking about a group of 10 things. We're choosing 6 of them. And because this is a P, this means that the order does matter. Again, that's what permutation stands for. So I'm going to take you over to a calculator and show you how to enter a permutation on it. Okay, so we are trying to do the permutation where we have 10 items, or in this case 10 numbers, and we're choosing 6 of them. Well, on our calculator here, and this is the Desmos scientific calculator that I've had you use if you don't have one of your own. Normally it's going to start you out on the main menu. You need to go over here to the function button, F-U-N-C. Then you're going to go down here to the bottom right, click on NPR. On some calculators, you enter the 10 before you click on your NPR. Then you enter the 6. So some calculators, you would do 10, click the permutation button, then enter 6, click enter. On every calculator, it's different though. Well, some are the same, but it could be different on everyone. On this one, you click the permutation button, and then in parentheses, you do 10, 6. So the number of items that you're choosing from comes first, comma, the number of items that you're actually choosing. In this case, it's 6. Then you would hit enter, and you can see that there's a total number of outcomes of 151,200. That means that's the total amount of lottery tickets that are possible based on these constraints. If you have a different calculator, we can talk about how to do the permutations during class. I'm not going to go through all the different ones. That would just make this video take too long. So if you're not using this Desmos one when you're doing your work, use this one for now. And then when we have class, we can talk about your own specific calculator and where those buttons may be. Okay, let's go back here. We are done with problems for this lesson, but I do want to go up here and just fill in one more thing. As I mentioned before, we're not going to focus heavily on what's going on in those formulas. The formula's up here. But we will need to be able to identify whether a situation is a permutation or a combination. If you can do that, then the calculator will do those formulas for you. If you maybe go into a statistics class or take another class where we have more time to focus on probability, we may explore those formulas a little bit more. And you can kind of see how they're built, what's going on there, what's the difference between the permutation and the combination formula. But for now, we kind of have too much ground to cover, so we can't really dive too deep into that. One last thing to mention, and this is important. Permutations and combinations cannot be used when items are allowed to repeat in a sequence. So if we looked at the license plate example up above, where we could have, the letters and numbers repeat, we could not use a permutation for that. We could not use a combination. We would need to use the fundamental counting principle. So when numbers or letters or things are allowed to repeat, you are not going to use permutations or combinations. Permutations and combinations, they're used when you're selecting a certain amount of items. Those could be numbers, those could be people, from an overall number of items. So, you've got 40 items, you're going to select 5 of them. Well, all 5 of those can't be the same one. They're going to have to be 5 different ones. In our lottery ticket, the numbers all had to be different. They couldn't be the same. So if you're allowed to repeat, you're going to have to stay away from permutations and combinations and use the fundamental counting principle. Okay, I think we're just right about at 30 minutes, so we're going to hold it here for today. As always, enjoy the rest of your day, and we'll look forward to seeing you for our next lesson with probability.